What's sort of one of the moments that made you really, really happy in science?
Especially when you discover something at that moment on this whole planet, you're the only person who knows that special thing that exists in the universe. So that specific moment makes you feel so special, and that drives me more and more to explore science.
I love it. Yes, same. All right, well, I'll stop talking and let you go ahead and share your slides with us. Thank you.
All right, so I'm going to talk about brain-computer interfaces today. Feel free to stop me, ask questions during the presentation. If you're shy and you don't want to speak up, you can still like write the questions in chat and Aubriana can say those questions out loud. So don't worry about it. All right, so I'll share my screen and just let me know if you see the PowerPoint. Do you see 11?
Yep. Yeah, we
Yeah?
see a PowerPoint.
Okay. So this is one of the very cool topics in science, I think, brain-computer interfaces. And if you watched Stranger Things, you already know about the powers, mind powers. So this topic is about extracting information from brain, feeding it into the computer, and making sense of what the brain is doing. And if you're a scientist in a lab working on this research area, this is what the setup really looks like. You'll have a person plugged into a machine with these tiny thingies called electrodes, and you're reading from their brain. And all these signals are overall fed to the computer, after which the computer will try to make sense of what the person is thinking and can give some sort of a feedback to the person as well about their brain states. So suppose if the person is super sleepy, the computer can tell them that, oh, you're very sleepy today. So all those information can be processed and it can be given back to the person. And this is a way to record from brain as well as non-brain. Any kind of signal can be achieved from your body. You can also measure your heart rate, for instance. So if you play video games, you can measure muscle movements. So those are non-brain signals which can also be fed to the computer. This is an example of how muscle movements are recorded. These tiny thingies are called electrodes. And you can see that there are wires plugged in. So this is measuring the muscle activity of this person. And these wires are feeding that information to the computer. And when we talk about brain signals, there are various ways to record brain signal. One of the ways, if you've seen this machine, it's called fMRI. And it essentially measures blood flow of the person. So the person will lie down on this slide and it goes in. And this is a giant magnet. And this magnet will try to make sense of the person's brain activity. What it really does is if the person is trying to talk, for instance, the brain area which controls the talking gets activated and a lot of blood flows in that brain area just so that they can activate that area. And that is detected by these magnets. Now, let me ask the question to you guys. Do you know like what is the relationship between the magnets and the blood flow? How can a magnet detect blood flow in the brain? Yes, Diane.
Because your blood has iron.
Very good. Yeah, your blood has iron. So iron movements can be detected by a magnet, and that's how really fMRI works. It just tracks which part of your brain is consuming so much blood that it is active. And that's how fMRI can figure out which parts of your brain are active. Another way to record brain signal is using EEG. And the setup looks something like this, where a person is wearing a cap and this cap has these tiny thingies over here called sensors, and they're plugged into wires like that, which are fed into the computer. And these sensors measure voltage activity of the brain. If you know a little bit about the brain, it's just made up of these cells called neurons, and these cells talk to each other using electrical signal. So it's almost like a battery underneath, generating some sort of electricity. And this electricity gets traveled between areas so that they can talk to each other. And this electricity is detected by these sensors. So that's how EEG works. Let me ask another question. Do you know why this is present on the person's face? Why are we recording from the cheek as well? No answers? So overall, these sensors are super, super sensitive. So apart from the brain signal, it can also detect any other signals. For instance, if you're blinking your eyes, it also gets added to the brain signal. So if you want to remove all those extra noises, which are not brain signals, you want to record something, an extra signal, which is not a part of brain signal. For instance, by doing this, you're recording all kinds of eye movements, which can be subtracted from the brain signal. So you can have like a beautiful clean brain signal. And EEG records, as I said, electrical activity, and it feeds to the computer to make sense of what the brain is doing. Another way to record brain signal is using light. So again, this is a setup where these thingies use infrared light to measure the blood flow. Again, it uses very similar principle as fMRI. It measures the blood flow, but fMRI is a huge machine, as you can see. You need to go to the hospital or the lab to record from your brain, but this thing is tiny. It fits into a bag. You can have it at home to record from your brain if you like. And one more way to record from the brain is using MEG, magnetoencephalography, which also uses magnets to record from your brain, but it doesn't use blood flow. It just measures the electric activity using magnets. And I have another slide where the content is a little sensitive. You'll see a person's brain opened up. So if you're sensitive about those things, I suggest you like don't look at your screen for the next 2 minutes while I talk about that content. So another way to record from a brain signal is opening up someone's skull and looking at their brain surface and implanting something called electrodes on the surface of their brain. So here you can see that there's a plastic sheet on someone's brain, and there are wires coming out of it, which are fed into the computer. And these tiny dots that you see over here are recording the brain activity from the neurons underneath. And this signal is so clean because all the other methods that you see are recorded from the outside of the brain. So overall, in a person's head, brain is somewhere inside, right? So the signal travels through so many layers of skin, hair, for instance. So it kind of gets weak by the time it reaches the sensors. But if you record from the inside of the brain like this, the signal is very clean, it's very beautiful, and you can figure out what the person is doing at a very high accuracy. And another way to record from inside of a person's brain, if you don't want to completely open up their skull, is to drill tiny holes and implant these electrodes. It's almost like a rod which is implanted inside the brain, and this rod has tiny measurement devices on it where you can record from inside of a person's brain by this process. And this is what it looks like. Each of these dots are electrodes, and they're recording the information from inside a person's brain, but this person has undergone this surgery. So the sensitive content is gone. If you're not looking at it anymore, you can start looking at the screen at the moment. Yeah. And finally, this is the most latest thing. This is called a Utah electrode, where we now have a capacity to record from single neurons in a person's brain. So this electrode is 2 micrometer big. It's super, super tiny. And each of these rods in the electrode record from a single neuron. And neuron looks something like this over here. It's super tiny. It's just 5 micrometers long. And each of these rods will record from single neurons in a person's head. And again, for this process, you need to undergo the surgery. All right. So before I dive into the applications, do we have any questions? All right. So the applications of brain-computer interfaces. The very first application is you can help people with locked-in syndrome or someone suffering from a disease called tetraplegia. In this disease, the person's brain is completely active, but they have full body paralysis. They can't really move their arms, legs, they can't really move their mouth to communicate with the outside world, but they're alive, they're thinking. So if they want to use their brain signals to communicate with the outside world, you can help them. And to do this, people usually put a screen in front of them with all these letters on it, and they're asked to focus on the letter that they want to spell. And when they focus on this letter, using their brain signals, the computer can figure out that, oh, this is the letter that they want to spell. And that's how the computer knows what they're trying to communicate. Another example of where you can help people is if someone has suffered some sort of accident where they've lost their hand or leg, you can use their brain signal to move a robotic arm. So you can use that in some sort of a prosthetic where you have a robotic arm and you're using someone's brain signal to move that arm. Another example is for home automation. Right now, if you've tried these devices, Google Home, for instance, you can use your voice to turn on and turn off lights at your home. But instead of using your voice, you can think of using your brain signal to do this. One other example is where you can use brain signals to help pilots or help drivers. So overall, if you're driving for like 12 hours, it's possible that you get sleepy and it may lead to some accidents. So if you want to avoid that, you can use someone's brain signal, constantly monitor how alert they are and give them some sort of a feedback that, oh, you're feeling sleepy right now, maybe you need to rest, you can't drive right now. So that sort of operator monitoring can be done using brain signals. And you can also help pilots for this because they have long flights and you want to measure their amount of alertness, amount of fatigue, and give them some sort of a feedback.
Prachi, we have a good question. Sneha is asking, wasn't this machine used to communicate when Stephen Hawking was suffering motor neuron disease?
So it's a very, very good question. So Stephen Hawking, the device that he had was a very quick speller. It wasn't a brain computer interface because this wasn't well developed at the time. The device that he personally had was a very good predictor. For instance, if he wants to spell something from S, he would just type S and the device would give options of spelling starting from S that were more probable that he's trying to communicate. And so he just had to click the word, select the word, and that would be spoken out loud. So at the time, that was the state of the art. That was the latest thing, and that is what he was using. So it wasn't brain signal per se. It was just his hand. It was just like a very good speller. But last week I was at this talk from Stanford where they now have the exact same device using the brain signals. So they were implanting these Utah electrodes in a human being, and they're able to spell things literally like whole words using brain signals. So yeah, we are there now in terms of science, but Stephen Hawking did not have that device per se.
That's very cool. And on that, could I add a question? So where do they know to put that Utah electrode? How do they know where to place it?
Very good question. So there are two main areas for this. Specifically, the Stanford study that I mentioned put it in the motor area where handwriting was driven. So in the motor area, in the specific area which was used for writing is where they placed it. And then they asked the person to imagine that you're writing a word. So the person would imagine writing A or W, and that's how the computer would know that this is what they're trying to write. But you can also implant it in suppose listening area, and you can ask the person to say, think of a word. So that audio of that word would be highlighted in the brain, and that's how the device would know that this is what they're trying to say. And I do have a demo for that later on where they use this for in the audio region of the brain.
That is so cool. Thank you.
And one other example where you can use this is for lie detection. For instance, right now, the methods we have measure a person's heart rate, for instance, or their perspiration rate to figure out if they're saying the truth or lie. And instead of doing that, you can think of using their brain signal to figure out if they're trying to lie or not. And of course, there is entertainment. If you're playing video games, there currently like we have motion detection sensors, but you can also think of like moving a person in the video game using your brain signal, for instance. And of course, I talked about a little bit about the health applications, like you can help people with prosthetics, but there's also this whole area of study where people try to figure out what is your brain state in sleep. And by that, they can figure out how good of a sleep you're getting. So even for sleep state recognition, you can use their brain signals. And there are a lot of medical applications, for instance, sleep disorders, or if a person is in coma, you can monitor their brain states and figure out how long they're going to take to recover, or what exactly you need to do to help them.
Oh,
There's also, yeah.
Oh, we have another question from your previous slide. Mamadou is asking, could this have a relation with virtual reality?
Very good question. So yes, it does have a relationship with virtual reality. A lot of science labs are collaborating where you can use your brain signal to move character in video game, for instance, in VR. And So in VR, you can also watch movies, right? It's almost like changing channels in your television. So instead of actually physically changing channels, you can think of changing channels in your brain, and then that is detected by the VR and it'll project something else based on the channel you want. So all these applications are, people are working on this right now.
Thank you.
So in terms of medical applications, if you, I don't know if you're familiar with this disease, epilepsy, where a person experiences something called seizure, where their cells in the brain starts becoming active without their want to do so. For instance, right now, I want to talk to you guys. So the parts of my brain that control speech are activated. But if I had this disease, the part of my brain that controls speech can randomly get activated during the day. So this can be fatal, for instance, if you're driving and imagine the part of your brain that controls your hands get activated and your hands start moving like crazy. That can be fatal and lead to accidents. So in this disease, one way to help the patients is to figure out which parts of their brain get randomly activated and perform some sort of a surgery to like deactivate those parts. So you can use brain computer interfaces to help these patients. And there are diseases like schizophrenia or ADHD where this is helpful. In schizophrenia, specifically, you hear sounds that don't exist, you see things that don't exist. So any kind of hallucination, you can help people with schizophrenia by deactivating parts of their brains. And this is done by stimulating the brain. So right now I've been talking about how you can record from the brain, but there is also an inverse process where you can stimulate the brain from the outside. You can apply some sort of a magnetic field or some sort of an electric current to the brain to make the brain active. And that way also you can help these patients. And of course, there's this whole neuroscience research in all these universities going on. We're trying to study how the human brain works. And specifically, the kind of questions that people study is how brain processes language, how brain processes visual information, how we make decisions. So all these areas of research people are working on. And I have a couple of demos for you guys from the lab and from this area. So let's play the first demo where this is the demo from the speller that I showed you earlier, where the person was completely paralyzed and was trying to spell on the screen. So let me see if this works. So do you see the YouTube video?
Yes.
Okay. So right now you'll see that there is a screen in front of the person and the person is trying to spell the letter F. And you'll see that all the letters get highlighted randomly and the person is asked to just focus on the letter F. And what really happens is whenever F gets highlighted, their brain goes, aha, this is the letter I want to spell. And that aha signal is detected by the computer. And that's how the computer knows that they're trying to spell F. So they're correctly able to spell F. And if I keep playing this video, they'll be able to spell the whole word free. But as you can see, this process takes a while. It's just one letter at a time. So it's a little slow if you want to communicate in real time. So we are developing like faster methods to do this. Another example is, this is a very cool example, where you can read from a person's mind in a way. So here you have an example of this kid talking to his friend on the phone. And suppose I, as a scientist, don't know what their friend is telling them, but I want to peek into their brain and figure out what they are listening to on the phone. So what I can do is record from this kid's brain, and whatever signals I get, I feed them into a computer and try to decode what is the conversation that they're listening to. So in this example, they're listening to some digits, and I'm going to play the decoded signal from their brain. So let's see what it sounds like. All right, so I'll play the sound and I'll ask you guys what you hear. So let me know.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
What do you guys hear?
6, 7, 8, 9, 10.
Yeah, you hear digits, right? Can you tell me whether it was a male voice or a female voice?
It was a male
I
voice.
think it was a male voice.
What a male
Male
voice.
voice.
It's amazing, right? You simply figured this out using someone's brain signal. You had no idea what the person was listening to on the phone, and using just their brain signals, you could figure out what they were listening to. And another example where you can use brain-computer interfaces is to help people with hearing deficits. So currently, if you have normal hearing and if you are in a very noisy place, say in a restaurant or in a cafeteria or in school, overall what happens is if you want to focus on someone's voice, regardless of what is happening in the background, your brain really focuses on that person's voice. Everything else is silenced in the brain. So you can just focus on one person's voice regardless of what is happening in the background. But if somebody has a hearing deficit, for them, all these voices, the person's voice that they're listening to, as well as the background voices, are equally loud in their brain. So they find it super difficult to concentrate in a noisy environment because all the sounds are equally loud in their brain. So you want to help them to make hearing aids smarter so that the hearing aid figures out what the person is trying to focus on and amplifies that sound only and shuts down everything else in the background. So you can do that using their brain signal. And I'll show you how that works. So let's see. Somehow my pointer is not working. Let me see if I can. All right. So in this example, what you'll hear is a male and a female voice. It's a mixture speech, male and a female simultaneously talking. And you'll be asked, the person is asked to focus on just the male or just the female. And when the person starts to focus on just the male, using purely their brain signal, the device figures out that, oh, it is the male that they are trying to listen to. And the device will amplify male voice and shut down the female in the background. And you'll see how that works.
How to be a shepherd. Dogs are great companions for a variety of people.
Especially when you know how
Have
to
you
do
ever
it.
thought about having your own
Shepherds
companion?
can be found all
If
over
you do
the
not
world.
have a dog yet,
Any
you
place
need to
from the
understand
desert
the difference between breeds before making a choice. The breed of a dog can have significant impact on its personality, as well as its size, health, and required maintenance.
And now the
For
person
example,
switches the attention to female.
long-haired breeds, like collies,
Move to Idaho or Wyoming. Buy a sheepdog. Some sheepdogs are better than others. You would do best to look on the dog market online or see if you can find a breeder.
It's crazy, right? You can just use someone's brain signal to figure out whose voice they're listening to and help them hear better. So these are all the examples I had. All the demos I showed you were from our lab at Columbia. And I'm happy to take questions if you have any.
Thanks so much. Yeah, let's open it up to Q&A.
Prachi, I have a question for you. This is going back to your when you have someone think about letters and spell them out. You showed how your screen flashes in various columns and rows. Why can't you just flash individual letters one at a time and pick up their signal when you hit that letter? Why does it need to be the rows and the columns?
That's a very good question. So overall, you could see how the screen was a grid. And if you flash one letter at a time, it's possible that there will be mistakes. But instead, when you flash the whole rows as well as whole columns, you can flash that letter F so many times that the computer can be 100% sure that this is the letter that they want to spell. Otherwise, if you flash them one at a time, you can flash F only once. So the computer can kind of make a guess that maybe it's the F that they want to spell, but the computer won't be 100% sure. If you have like 10 instances of F flashes and their brain going, aha, computer can be 100% sure that, oh, this is the letter that they want to spell.
Gotcha.
Prachi, I had a question. So has anybody tried using any of the methods you showed of recording, information from somebody's brain to like recreate their dreams? So could you use any of these methods and watch them while they're sleeping, and then, right, because they're imagining their dreams, could you recreate them afterwards and then kind of show them what they were dreaming of?
It's a very good question. Currently, all the sleep studies only can predict whether the person is dreaming or not, but specifically in dreaming, what they're seeing is not done yet. So we're not there yet.
Thanks. We have a few questions in the chat. That's awesome. Crystal asks, can an interface be used for neurodegenerative diseases such as Alzheimer's?
To help the disease?
Let's see. Crystal, would you like to clarify?
Yeah, to like help the disease or like help those struggling with it like severely.
That's also a very good question. Yes, people are trying to use brain stimulation to achieve this, where you can like place some sort of an electric current in their brain to activate the areas that are dying out. So people are trying some sort of a brain stimulation, either with electricity or with magnetism, to help people with brain diseases. Specifically, I know that for depression, magnetic stimulation is very effective. FDA has approved it and people are using it as a therapy. And even for Parkinson's, where a person experiences some sort of a tremor in their body, they cannot control their limbs very well. So for that disease, electrical stimulation is used currently. So yeah, people are using these type of devices to help people with Alzheimer's, Parkinson's.
Thanks. And we have
Any other questions?
Yes, we have a question from Mamadou. How can colors affect how the brain thinks?
Very good question also. So brain has a whole system just to detect visual information. So the back of your brain processes all the visual information, and it has cells that are tuned to certain colors. So if you see a specific color, only those cells light up, and that really activates very specific regions of the brain based on what color you're seeing. Did I answer it? Do you have more questions?
I have a question. So can we, for the external stimulation, can we only stimulate neurons sort of on the outside of the cortex versus more embedded structures like the hippocampus?
That's a very good question also. So both, you can do both. There are devices on Amazon which help you like stimulate your brain. Do not buy them. They're like commercially available at the time and they're marketing it as, oh, we can help you focus better before your exam if you use brain stimulation. So that's how they're marketing it. But I don't think those work. So you can stimulate from the outside of the brain, but they're not very good because when you stimulate from outside of the brain, it kind of targets a large part of the brain. So it's not really helping. I don't think so. But all these studies that I talk about where you're trying to help patients, they stimulate from inside of the brain. So they kind of undergo a surgery and can stimulate a pinpointed location in the brain if it is electrical stimulation. If it is magnetic stimulation, you can stimulate from the outside and target a pinpointed area, but it needs to be done in the lab. Do not buy those devices on Amazon.
Oh, and we have another question from Victoria. Let's see. Can using this type of technology help in other areas such as the law? Like, can studying someone's brain detect whether they're innocent or guilty?
Yeah, you can. So you can think of how your brain is activated differently when you're trying to lie versus when you're saying the truth. So if you know the science behind it, if you know which areas of the brain are highlighted when you're lying versus when you're saying the truth, you can use that for lie detection as well. So you can help with the law.
Very cool. And another question from Melanie. If the ECOG things in your brain cause, she's asking, do the ECOG things in your brain cause damage to your brain?
That's a very good question also. So people don't voluntarily undergo these surgeries. ECOG, just to remind everyone, is the method of recording from the brain where you're opening up someone's skull and implanting electrodes on the surface of the brain. So nobody undergoes these surgeries just voluntarily. They do this for clinical purposes, specifically if they're suffering from epilepsy, where parts of the brain get like active randomly. To deactivate them, surgeons need to figure out which parts are active. And to do that, they undergo the surgery and implant a sheet of electrodes throughout the brain and figure out which parts are getting activated randomly. And so this is a clinical process. It's done to help with a disease and not for the research. But you can, like, once these patients are implanted, they also like help with the research. Like they do all the experiments we designed with.
That's really interesting. I didn't know that they have to sort of do a test detection first, and then you can pinpoint.
Yeah.
That's a lot of intense surgery.
Yeah.
a question. Okay, so it's about surgery. It's the seizure that they are going to suffer from seizure at a certain time.
Yeah, so it happens randomly. They don't really know. So specifically with these patients, surgeons implant these sheets on their brain, and then the patient is supposed to stay in the hospital for a week because they don't know when this is going to happen. So they're just waiting for the seizures to happen so that the surgeons could figure out, oh, this is the region where this is happening. So really, you don't know when it's going to happen. You just have to wait for it to come up.
So I've heard that flashing lights can sometimes stimulate seizures in people as well. Is that because like that part of the brain is close to whatever part of the brain is dysregulated, like the part detecting light as well?
That's also a very good question. So overall, like uncomfortable stimuli in the environment can trigger seizures. It can be visual. It can also be audio, because it's a funny story. Like I designed an audio experiment to run with these patients, and my professor made a joke that maybe if they listen to this, they'll start seizing, and that actually happened. So I felt bad. I felt bad for the patient, but this happens all the time. Like if they are in an environment with a little uncomfortable stimulus, it's possible that they start seizing.
Mm.
But in the hospital environment, it's a good thing so that they have to wait less. Otherwise, they're there for a week for no reason. Like they need more seizures to come if they're in the hospital.
I see. So they have immediate care right there.
Yeah. And the whole point, the whole reason why they are in the hospital is to figure out where these things are happening. So the more seizures that happen in that duration is better for the surgeon, so that they can like really, really pinpoint where this is happening. Do we have more questions?
I can ask
All
you
right.
a background question. How did you decide to join the lab that you did?
That's a good question. So my journey was like I first started working, like I knew that I wanted to do something in neuroscience. I just didn't know which area and what kind of work I wanted to do. I started with animal work actually. So in neuroscience, people don't just study human brains like I gave you examples today. They also study animal brains. The reason being, you can pinpoint more things in animal brains. You can do more experiments on animals. Of course, this is happening in a very controlled environment. But I started with animal lab, where I was trying to study how the rat brain functions. And I had to do all the surgeries that we saw today, like the ECOG that you saw today. I used to do that in animals, but I found that was like really stressful work for me. So I switched to human neuroscience, where I don't have to do the surgery. I can just focus on the science part of it, and a neurosurgeon does the surgery. So I like switched from the animal to human work after that.
Did you ever have any interest in brain surgery?
In human brain surgery?
Mm-hmm.
I think it's too stressful for me to like do surgeries on people. Like if you make one mistake, the person can die. So it's just not the area that I want to focus on.
Mm-hmm. I completely understand. Oh, we also have another question. Are the same kinds of machines used to study animal brains as well?
Yeah, exactly same kind of machine. It's just less sterilized. Because with humans, everything has to be like super sterilized. You cannot reuse the electrodes, for instance. With animals, it can be performed on a lab without a medical person present. Like I was a grad student doing this on animals. So in terms of the devices, it's almost the same. It's just you have to be a lot more careful when you're dealing with human beings.
Do they have small versions of MRI machines?
Yeah, they do, I think. I never use them. I always use the surgical things like the ECOG thing, but they are all smaller versions of what we use in humans. So,
Oh, that's really cute.
what inspired you to study brain-computer interfaces? I think this is like a very important field in the next like 10 years. It's going to be super important. I don't know. Did you guys see the Tesla video that came out? Neuralink thing? No? So Elon Musk has put so much money into brain-computer interfaces, and that small company is called Neuralink. And they're trying to make all these devices like the high-tech version of these devices where you can communicate using just the brain signal. And I think it's a really booming area. It's going to change how the world works in like next 10, 20 years. So it's, I mean, I would highly recommend you guys to see that video. I mean, I think it's a little exaggerated. A lot of scientists got mad because science is not there yet. And he's like giving this whole vision of how the brain will work, like how the BCI will be functional in the next 20 years. So, but still, like it's a good video. So. Do we have more questions?
Yes. What was the first experiment you ever did in the neuroscience field?
It was so bad. You really want to nothing worked. I think I did everything wrong. So the very first thing I did was I wanted to see how the brain changes while meditating. So you know how all these sleep studies are done, and they have like this whole paradigm where you know that if you're in stage one of the sleep, stage one for sleep, you have very special types of brain rhythms as compared to stage four in sleep. And I wanted to do that with meditation also to figure out like if you're in stage one of meditation, stage two of meditation, what happens in your brain. But I was like a stupid kid at the time. This was 6 years ago. I didn't know what I was doing and nothing really worked. So that was the first study. Like in terms of idea, it was a good idea, but nothing worked at the time. And this is very normal for science. Like the first 2 years you don't know what you're doing, like you'll get the hang of things later on. So
Do you think as we keep using these brain computer interfaces and we learn more and more about the information in a brain, do you think we could replicate a brain in a computer state? So if we understood every connection and how every neuron in a brain communicated, do you think we'd be able to replicate it one day in a computer?
yes, because so currently human brain is a lot more complex, but they've done this for a fruit fly, which is this big. So it has like only set number of neurons, and they kind of mapped all the connections of the fruit fly brain. It's called fruit fly brain project or something. You can look it up. They've done it for the fruit flies for sure. So you can think of it happening for humans as well. But also it's weird because human brain is so different. Like even if you look at the brain of identical twins, the connections are different and it's not driven by genetics at all. So I don't know how it can be customized from one person to the other. Did you attend a separate school just to study about the brains? So Sneha is asking if I attended a separate school just to study about the brains. That's a very good question and reminds me about so many things. So I initially, my first undergrad was in electrical engineering, which had nothing to do with brains. I used to work with circuits and signals, which has nothing to do with neuroscience. But I knew that I wanted to get into this area at the time. And so I sent like 400 emails to university professors that I wanted to work in their lab, and a couple of them responded. So I applied to the universities and applied to the master's program in those universities and switched from engineering to neuroscience after. But so this is also a very good example. Like doesn't matter what you get your undergrad into, if your interests are different than your bachelor's, for instance, you can always switch fields. And I've known like a couple of directors in neuroscience institutes that have nothing, like their degrees are not related to neuroscience at all. So, I mean, the specific person I'm talking about is Barbara Schinkerinheim. She is the director of Neuroscience Institute at Carnegie Mellon. And her degrees are electrical engineering, for instance, and biomed engineering. And it has nothing to do with the field that she's a director in a university. It's always possible to switch fields if you like. Do we have any other questions?
Victoria has one. If one is interested in studying neuroscience, what do you recommend to study or do?
So if you want to do research in neuroscience, the kind of work that I talked about, it is not just the biology part of the brain. Because you're recording from the brain, it can be an electrical signal. So you need to learn about like coding first of all, because all these signals are processed in the computer, and you'll need to write some code to get information from the signal. So that is, programming is sort of a base of any kind of science. And you can always, it's not that difficult. You can always Google things and learn. That's how I did it. So programming is for one. And if you're getting into neuroscience, my suggestion would be to work with machine learning or artificial intelligence, because those are the fields that help you extract information from the signal, from the brain signal. And these are the fields that are helpful regardless of neuroscience. Like even if you go into astrophysics, you'll be working with space signals. So to extract information from those type of signals also, you'll need machine learning, artificial intelligence. So programming and machine learning are like crucial regardless of what field you go into. But after that, you can think of like signal processing. Signal processing is a part of electrical engineering, which is helpful if you're looking at brain signals, and also psychology, because with neuroscience, you'll be designing a lot of experiments to extract information from the brain. And this experiment designing is a specialty of the psychology field. So that also helps. And of course, there's neurobiology for neuroscience. So these are the fields that are connected.
Going off of that question, Prachi, do you recommend that students try and get involved in research if they're interested in this? Because you said you studied something completely unrelated in college, and clearly it worked out for you. So you had other paths that helped you get there.
Yeah, so that is also a very good question. And yes, so once you get into research, you kind of get a sense of what it involves, what a PhD program involves. Doesn't matter if it is neuroscience or something else. Overall, the steps you carry out in research are kind of overlapping, and it would help if you do any kind of research. And I was trying to look up this website. So there's a journal called Frontiers, and they have a kid journal for teenagers and kids. I'll share it in the chat. And what they do is any kind of science that gets published, all the new science, they're converted into a kid language, which is accessible for high school and middle school students. So all these articles are converted into that language and published it in this website. So all the newest research is on this website if you want to go take a look. So somebody's asked, have you created a machine for the brain? So my research is to extract information from the brain rather than creating the machines for the brain. But there are people working on it, because the examples I gave you involved a lot of machines to record the brain signal. There is fMRI, there is EEG, there's ECOG. All these machines are created in labs also. So there is a whole bunch of people working on the machine part of it, which are mostly engineers. But my own personal research is to extract information from the brain and make sense of it. So that is the neuroscience part of it. There's one more question. Can neuroscience improve your thinking or help you learn something quicker or faster? So that's a very good question. Yes, it can. There are a lot of tricks. So I'm not like an expert in this, but I know that there are tricks that you can like follow to help learn things faster. For instance, if you've watched Sherlock Holmes, he had that mind palace thing to help him remember better. So you can have like these type of tricks to make your memory better, or make your thinking better, or your cognitive skills better. Is there any way to participate in the study and research of neuroscience if you still are in high school? So there is a way. At least I know of only one program at Columbia. It's called Brainiac. And if you apply to that program, they pair you up with a researcher at Columbia, and you work on a science project with them over the summer, I think. I'll probably type the program in chat if you want to take a look and apply to it. But I'm sure there are more programs than just the one that I know.
Yeah, and going off of that, for any high school student interested in getting into research, this is something that you can ask your guidance counselors about. And a lot of them, I'm sure, have like sort of a treasure trove of knowledge of programs like that. You just need to do the digging yourself. So I really recommend asking around getting into research sort of takes putting in some upfront work and energy and trying to figure out what's out there, but it's worth it.
Yeah, so giving my own example, I sent 400 emails to get this position at Columbia. So like do the work. I think it's completely worth it. Do the digging. Is the brain activity of a person who's good at a specific area like math look different from someone who's not good at math? That's a very good question. The answer is yes. So scientists have studied brains of, for instance, musicians versus non-musicians. And then they see that the part of the brain that processes music is larger in musicians as compared to non-musicians. So whenever you gain a skill, the part of your brain that is used for that skill has more connections and more neurons. So yeah, the brains do look different. So that's also like a very solid measure of like, if you're trying to better yourself, your brain completely changes. Do we have more questions?
So is it right that we still don't know exactly how many neurons are in the human brain, right? And that's a factor into, because you can have expanding in a different size parts of the brain as well.
Yeah, over your lifetime also they change, so we don't know. And even if you have neurons, it doesn't necessarily mean that that they're active. For instance, people who are born blind, their whole visual cortex has nothing to do, right? Because their vision is not being processed. So scientists have found that specifically for those type of people, that area of the brain processes other things. For instance, it also helps them process sounds better because their sound processing ability is a lot sharper than normal people, because that's what they rely on. So brain is really plastic. Like, it completely changes based on how much work you're doing and what kind of work you're doing. So over your lifetime, it's like kind of essential to keep your brain active, do more math or do some puzzles, and it really helps your brain. Any other questions?
I guess we could go ahead and wrap up. Thank you so much, Prachi, for being our first speaker. This is really, really awesome. And thanks everyone for coming. Melanie, thank you. Oh my God.
I had a lot of fun giving the talk. So
yeah, this is very, very cool. And so we're going to try to have more of these in the future, and more speakers from Columbia grad students. Yeah. Thank you all so much for your time today, especially on a beautiful Saturday.
Thank you, Prachi. That was great.
Yeah,
Thanks, Prachi.
Thanks.
Thank you.
Have a great rest of your day.
Bye, everyone.
bye, everyone.
Thanks for today's seminar.
Thank you so much for coming.
Thank you. Bye.
Thank
Bye.
you.
Bye. Thanks for the info.
Thank you. Bye.